Like anything in life, concentration is really going to be a matter of finding the sweet spot. We don't have to deal with a whole lot of nonsense and a whole lot of complication, but we can still get done the work that we'd like. Now, for that, I wanted to highlight something using this graph that actually shows two separate cases. These are two separate cases. I want to emphasize that. Where we have KOH or we have HBr. Notice strong base and strong acid in solution. Now, this is something that comes up a bit in the workshop that we get through. And I also want to point out this axis. We're in negative log of concentration. In other words, we're at 10 to the minus 2 concentration through 10 to the minus 10 concentration. Now, I've said that we don't want to be in too concentrated of a solution because now we have to care a lot about activity coefficients. We don't want to be there because we have to deal with fraction of association and dissociation. So we try to avoid really high concentrations. At least when we're doing the actual work. For our stock solutions, we love that because now we can have a high concentration where we really know the exact concentration well because we have lots of mass in there, we have lots of volume there. We've got a nice big stable stock solution that we can just dilute down to whatever we want anytime we want. We love that. But for our day-to-day work, when we're actually doing the measurement, we want it to be more dilute than crazy dilutions, concentrations of 1 molar, 10 molar. Those are good stocks. Those are not good working solutions. Now, when we're at these fairly high concentrations, remember, this is going to be just a negative log that we'd be talking about decimal place. Here we are. So that's the kind of concentration we're talking about right there. It's 0.01 molar. When we get out to here, we're talking about 1 times 10 to the negative 10 molar. So we're at some pretty big ranges there. When we're at reasonable working concentrations, you'll notice that this trend looks very linear, and so does this trend. They're very well behaved. Until we get down to about 1 times 10 to the minus 6. Right about here, all of a sudden, we see that things kind of start to curve a little bit. And in what might be a surprise to us, if we're not remembering what we saw in the workshop, all of a sudden they take a bend so they can level out at 7. But let me remind you of why. If we take one molecule, and I'm going to be very specific about this, let's take one molecule of HCl. Let's put that into 1 liter of water. You can see that that's going to be incredibly tiny. That would be, 6.022 times 10 to the negative 23rd moles divided by 1 liter. So this is going to be to the negative 23rd concentration. So we're way out here. So we'll use this as a super extreme case, like way over here on this plot. What is this bias? Well, if I have totally deionized water, pH 7, right? If I add in 1 ion of H plus and 1 ion of Cl minus, what concentration do I expect that to be? Super tiny, like we just said, molarity of about 10 to the minus 23. So what should that actually do to my pH when I add that to the autoionization of water? Nothing. One molecule added to what's already autoionizing out of that 1 liter means I should really expect this to be pH of 7. And so if we're at very, very, very dilute concentrations, we always expect it to end up being pH 7. So somewhere in between the two, though, we now have to consider autoionization of water and how that's going to entangle with all of our other variables that we have and all of our other chemical equilibria. And we get to use our favorite systematic treatment of equilibrium. So we have to be very cautious in this concentration range. Experimentally, we're almost always going to try to stay below where we have to care about activity coefficients a lot and where we have to worry about systematic treatment of equilibrium. And so you'll see that our favorite working conditions in analytical chemistry kind of end up being molarities of 1 times 10 to the minus 3 through 1 times 10 to the minus 5. That's kind of our sweet spot. for having a nice, simple, easy life where we actually get to go home and see the wife and kids. Now, that said, still think that you're ready to go? Still think you can handle the most hardcore analytical cases around? And that this range is going to be fine for you? Well, let me remind you of something. When you have a really good pH titration, you've nailed your endpoint, it's very close to your equivalence point, you've got that very faint pink color of phenolphthalein, and I've mentioned you can just breathe across the surface, and when you do, that little bit of carbon dioxide dissolving in the water will back titrate things. Picture how tiny of a concentration that is. If you're working this regime, you're actually caring about carbon dioxide becoming carbonic acid. Oh, there we are. My handwriting just got terrible. H2CO3. In other words, just atmospheric gases are going to be able to throw off your measurement. I'm not saying they're impossible, but these things are really nasty to do. And so, for routine work, when you're not trying to show off, you're not trying to do something extreme or exotic, you're going to stay in that sweet spot regime as much as possible.